I want to start the video today with this question. How could you describe a three-dimensional object to a being that lived in only two dimensions? So let's say that somehow you were able to have a conversation with a cartoon character that had spent their whole life living on a flat sheet of paper. How would you describe a three-dimensional object like a soccer ball to this two-dimensional being who had no notion of what three dimensions might look like? And this might seem like kind of a funny intellectual exercise to you, but this is an important thought process for a mathematician to go through, because in math, we don't just study things up to 3 dimensions, we study 4 dimensions, 5 dimensions, n dimensions. And it's important to think about this going from a 3D to a 2D, because it might help us come up with ways to be able to picture 4-dimensional objects or 5-dimensional objects if we think about ways to reduce the dimension backwards 1 or 2 levels. All right, so there's one way that we already know how to describe 3D objects in a 2-dimensional fashion, and that's a topographical map. So we know that these topographical maps are created by kind of slicing a mountain at differing elevations, and they make these sort of curves around the edge of the mountain, and then we project those down onto a flat map. So these topographical maps tell us over here on this topographical map where the lines are really close together, that the mountain is pretty steep in that part, because it means that as we went up a level of slicing, we didn't go in that very far. And so that must be a pretty steep side of the mountain. But then over here, where the lines are a little bit further spaced apart, that must come from a gentler slope, because as we moved up, the mountain moved in quite a bit. In math, we call these curves on the 2-dimensional graph, we call these the level curves of the surface of the mountain. Right, so we'll think of our mountain as being a function, z equals f of xy, and the level curves are the curves in the xy plane, so that's our topographical map, the xy plane down there, with equations f of xy equals c. So essentially they've taken f of xy, or z, and replaced it with a constant. That's that plane that's parallel to the xy plane. And we're slicing the mountain for different values of z. All right, so let's try our hand at drawing a topographical map of a 3-dimensional object. And we probably don't even know just off the bat what this object actually looks like. Okay, so we were asked to sketch the level curves of this function for c equals 2 and c equals 4. So remember, the c is the value that you're plugging in for z. So those values are going to go here and replace it. We're just going to be slicing with those constant values of z. All right, so I'm going to start with my c equals 2 that they gave me. And I'm just going to replace f of xy, or the z coordinate, with 2. And we're going to see what kind of 2-dimensional curve falls down onto the xy plane. All right, so I'm going to rearrange this until I recognize what it is. I'm going to square both sides. And that gives me 4 over on the left, and x squared plus 4y squared. Okay, so it kind of has a conic section feel to it. Those coefficients are different, so probably an ellipse. Let's get 1 on the left-hand side. Usually we have the 1 on the right, but we're going to divide both sides by 4 to make this equal to 1. So I get 1 equals x squared over 4, and then the 4's cancel for the y squared term. Okay, it's easier to look at that like we usually do, like x squared over 4 plus y squared, and put the 1 on the right. All right, so that's an ellipse. And so remember that this number down here means that our x radius is equal to 2, because it's 2 squared, and there's a 1 underneath the y, so the y radius is going to be a 1. So I'm going to draw myself an ellipse here. I'm going to go 2 in the x direction and 1 in the y direction. I'm just going to fill in an ellipse here. All right, and I am not exactly an artist, so I'm not going to expect you to be. So that's elliptical enough for me. All right, so let's see what we get when we plug in c equals 4 over there for f of xy. So I get 4 equals square root x squared plus 4y squared. Again, keep rearranging it until it looks familiar. Square both sides. And let's divide again. This is going to be another ellipse. Okay, so I get the 1 on the left, x squared over 16. The 4 and the 16 will reduce, so I'll get y squared over 4. And again, this is giving us an ellipse. The x radius this time is going to be 4, and the y radius is going to be 2. right, so let's go 2 in the y direction and 4 in the x direction. All right, so a bigger ellipse. All right, so there's our very limited topographical map of this surface. Let's go take a look and see what the surface looks like. All right, here's our surface, square root of x squared plus 4y squared. And we were slicing it with the plane z equals 2. And we got a curve that intersected there. And if I kind of rotate this to where it looks like I'm projecting down onto the xy plane, you can see that ellipse that we graphed with an x radius of 2 and a y radius of 1. All right, so that was our first value we sliced at. And then we had a plane go through z equals 4, which cut us a slightly larger ellipse, x radius of 4, y radius of 2. So it looks like we did a good job on that one. All right, and you could see if we had done more of those, then maybe those level curves might give a two-dimensional being an idea of what this thing might look like in 3 dimensions, even though it's not something they could actually picture. The last thing that I want to show you in this section is functions with more than 2 variables. So this is a function of 3 variables. So your input comes from a point in R3, x, comma, y, comma, z. You plug into this function, and it's mapped somewhere into the 4th dimension. All right, so over here, instead of being another name for z, because z is now one of our variables, this is another name for w. I don't know, we ran out of letters, all right? So we can't really picture what this function looks like because we live in 3D. We can't picture what 4D looks like. So if I can't see it, what's the point? All right, but this function is actually an interesting function. This function gives you the energy intensity at a point out in space, x, y, z, if the source of the energy is located at the origin. So imagine some kind of energy source is radiating out energy from the origin, and you're floating out in space at some point, x, comma, y, comma, z. This function is going to give you the intensity of energy at your location, right? And I just picked this number 10 up there. That's a constant that depends on the kind of energy source, but 10 is a nice round number, so we'll just use it. All right, so to get an idea of what this function looks like, we're going to use the same kind of idea as a level curve. All right, so we're going to do the same thing we did for level curves. We're going to replace that f of x, y, z with a constant. And I'm just going to use a generic constant, c. And we're going to see if we can recognize what comes out. So for a function of 2 variables, what fell out was a level curve in the xy plane. Now what's going to fall out is a level surface in R3. So I'm going to rearrange this equation like we did in the last example until I recognize it. I'm going to multiply both sides by this denominator over here so I can get it out of the denominator. All right, so I end up with c as a coefficient of that, c times x squared plus y squared plus z squared. And I'll just have 10 left over on the right. All right. And c is just a constant. It's a number like we were plugging in 2 and 4 in the last example. So I'm just going to divide both sides by c. And we get x squared plus y squared plus z squared is equal to 10 over c. All right. It's been a while since we thought about this kind of equation, but that's the equation of a sphere. And of course, the size of the sphere depends on what that value of c is. But let's go graph a lot of these spheres and see if we can see what it tells us about this intensity energy function. All right, so GeoGebra is good, but it's not so good that it can show us what a 4-dimensional object looks like. So we have our 3-dimensional level surface here, x squared plus y squared plus z squared equals 10 over c. And I've got c set at 0.19 right now. So remember what this is representing. We said we had an energy source at the origin. The c was the function value, the intensity that you're feeling when you're at a particular point out in R3. All right, so if you are on this big sphere here, then you are feeling an intensity of 0.19, whatever units you measure that in energy in. All right, so as I increase the value of c, look what happens to my level curve. Okay, it shrinks down and down and down. And so now if you're feeling an intensity of 2.44, you're on this smaller sphere, which means you're closer to the source of energy, which makes sense, right? When you're closer to the energy, you're going to have a stronger intensity. So as we increase this value of c, as we slice this 4-dimensional object with a 4-dimensional plane, I don't even know what that would look like, all right? But it's going to give us this level surface that says as the intensity increases, that means that your XYZ coordinate must be closer to the source of the energy. All right, so that's it for section 12.1. 12.3 is our next section in class, and we're going to learn about partial differentiation.